C'est bon. Okay, welcome back. So we've seen trees. Essentially, we start from all the data points, and we separate in two according to the criterion over there, and then we continue separating until a maximal depth or a minimal number of points per leaves. Typically, we end up with a predictor that's not so good, I would say, not so great in terms of performance. And which has a high variability. So the idea is that you don't just use one tree in practice, one carefully suited tree, but you use ensembles of trees. And there are two ways of using ensembles of trees. So this is really ensemble methods. And what I'm describing here is is particularly relevant for trees which are weak learners, so not so good learner with a high variance. But it can be applied in spirit to various other methods. I mean, aggregating predictions. The first method is a random forest, and for that I need to talk about bagging and aggregating predictions. So if you had capital M independent data sets, which you don't, sometimes having one data set is already a challenge, so having capital M of them is even more a challenge. So maybe in this case, what you could maybe do is to aggregate the predictions from the predictors on each of the data sets. So f theta hat little m of x. So you would train on each of the data sets and aggregate that. So for k nearest neighbors, for instance, it consists in taking your full data set, you separate into capital M1s, and then you have a KNN predictor for each of the data sets, and you aggregate the prediction from them. It's not like you have much to gain from there. You could wonder, well, what if I'm using just the full data set compared to the smaller data sets? And for k nearest neighbors, I mean, there is no gain in that except that you can do things in parallel. Where things start to be more interesting is when you have something called bagging. So that's for bootstrap aggregation. Does anyone know about bootstrap here? Don't be shy, express yourself. So bootstrap aggregation. So great news, no one knows about it. So so bootstrapping is when you have one data set D of size n, and you're going to recreate data sets from there. And so you're going to create M data sets by sampling with replacements. M data set by sampling with replacement. So it seems like you will have data sets that will be rather similar, that will have some similarity. And also you will have points that are repeated in data set. So you have n data points, you sample n data points with replacement. And so various data points will come in twice, maybe more. In fact, you have a fraction of, I mean, you can look at the fact. You have that about 37% of the data points are not present in the data set. So if you take one data, of course, if you take one of those data sets that you create by sampling with replacement, it will only contain essentially 2/3 of the data points. And the small computation for that is that the probability that a point is not selected is 1 minus 1 over n to the power n. So at each consistently for the n time when you're trying to get one point, you're avoiding this one. So the probability that you're never picked up is 1 minus 1 over n to the power n. And so this converges to 1 over e. And so the probability, I mean, that's the 30% of the points which are not selected. Bon. Fact. Good thing is that when you don't have points which are present in the data set, you can use them as a validation set. So, I mean, nothing is lost in the big, in this machine learning paradigm. Okay, so I'm having, so I start from a set of data points. I'm creating M sets like that. And then I could aggregate the predictions from there. And so random forest goes one.
They are much smaller than.
No, they're also of size n. And that's why I'm saying that they have repeated entries. So because you only have 2/3 of the data points, so some of them need to appear at least twice. And so random forests, it mixes various things. So first, this bagging idea, meaning that each tree in the forest will be trained on one of those randomly sampled data sets. So that's so I'm sampling. So if I have a forest of capital N trees, I start by having capital M random data sets obtained by a bootstrap like that. After that, the next thing is that I have a random projection, meaning that I only allow for certain cuts randomly. So I'm not going over all cuts here, between 1 and D, but say at each step I'm only allowing a certain I'm only allow myself to choose a certain number of directions in which I'm cutting. So like I'm choosing 5 directions out of the 1,000 possible directions, and those 5 directions are selected at random for each node and are different from one node to the other. That's so, and you mix those two, and the idea here is to have something that increases the variance. So in the end, I mean, for this method of aggregating predictors, I mean, this works better. Somehow you get a better estimator, so with smaller variance, if your predictor are as decorrelated as possible. And so random forest, I mean, you're trying to put in as much randomness as you can. So you put randomness in the data set and in the way that you're cutting, so that in the end, the predictions are as different as possible. And so typically you're doing that with the trees that are relatively small, say depth 2 or 3, and maybe a significant number of minimal points at the leaves. And so each of the tree that you get is pretty bad because it doesn't really see all the data and you haven't allowed for all the projections. But by this kind of aggregation of you get some wisdom of the crowd and you get something which is a much better predictor. So that's all I will say about random forests. And there are world-class specialists of random forest 2 corridors from here, Gérard Bio, if you want the name. And so there is now some mathematical analysis to understand why this is working. So that's the first ensemble method. And I'd say that the feature that can be kept here for other methods is this bootstrap idea of having various data sets. Another ensemble method relies on boosting. So here I will present XGBoost, which is really efficient prediction method for regression in general context. And so it relies on boosting. So boosting it's a greedy procedure. It's a greedy procedure to come up with a good predictor, to come up with a predictor as a sum of elementary predictor, So here the idea as well is that maybe we don't go for like the one ideal predictor. Maybe we sum a few of them that are typically weaker predictors. Not as great, but when you average them, when you average ideas, the advice, then you get something that's more robust. So typically we're looking for a predictor of that form, f capital T of x. Capital T will be a parameter describing a certain number of rounds or iterations. And this will be the sum for t equal 1 to capital T of alpha t ft of x. And so this will be some elementary predictor. So typically, in the context of trees, I'm thinking of really a small tree, depth 2 tree. And so I will be summing up predictions of depth 2 trees. And the way it works, and so the general philosophy, somewhat ideally, what you would want is to find, is to iteratively find the parameters with a greedy procedure, meaning that you start by fixing f1 and alpha 1, and then you fix f2 and alpha 2, and so on and so forth. And so somehow at round t, you're looking for what? You're looking for parameters for which you minimize the empirical risk. So here again, I'm not explicitly considering a regularization term because I'm thinking of trees and have other ways to regularize. But what I'm saying could be applied to methods where you have regularization terms included here. So yi ft minus 1 xi plus alpha f xi theta. So I'm looking, starting from some current function ft minus 1. So typically you would start from f0 equals 0. So first round, you're looking for some prediction function alpha f that somehow best predicts y. And at the second round, you start from the function f1, which would be alpha 1 f1, and you're looking for the term alpha 2 f2 to add to that in order to improve the prediction, to best improve the prediction from there. Is the strategy clear for everyone? So you start from nothing, then first predictor, then you add another one, and so on and so forth. And so in principle, you're looking for a parameter alpha here that minimizes this linear combination, and this prediction function is also parameterized by parameters theta, which for trees would be the various regions and the prediction in the various regions. So that problem is not so easy to solve. In general, you cannot solve it exactly. Yeah.
But these parameters, they are associated only with the f function that you're trying to get the alpha for, or they are also used in the previous one? The theta.
The theta. No, it's not only for the new function.
So it's like you have different parameters for.
So maybe here, I mean, I should write it like that.
Yeah, yeah.
And so let's, I mean, so the general, there are two ways of doing boosting, either doing it directly on the value function here or do it on the gradient. In fact, regression boosting is a bit in the middle. It simplifies a bit, but so I'll still present the kind of general approach. So let's consider something that's called the gradient boosting. So for a general function, so here, this elementary loss, it's a general function, but I'm typically thinking of Lyz being like y minus z absolute value or y minus z squared, if I have one-dimensional inputs. And so the idea of a gradient, maybe let's first do a least square boosting, because that's a situation when you can write things analytically. Je l'écris, voilà. So for here we introduce RIT, which is the residual of the residual for the prediction. So that's what you cannot capture with the prediction you currently have. And then alpha t, theta t. So here we're in a situation where L yz is equal to y minus z squared. And so then alpha t theta t is the argmin of the problem of 1 over n sum for I equal 1 to n of RIT minus alpha f xi theta up squared. Something like that. So it's really the usual least square fit of RIT by f xi theta. Well, and if I have trees, then I don't even need the parameter alpha here, because trees, and you will be directly adjusting it. So this means that well, I don't have the. Maybe let's do a mock example. I mean, there is a picture in the book by Murphy which makes things more clear. But so imagine that I have this kind of 1D space. So it's really just x1. And here I have my labels. And I'm using trees to predict this. So the tree, presumably, if I have maybe the tree is predicting something like that. You know, if I have 3 regions, then maybe it will give something like that. So then we will, from there, compute the various, the residuals here, there, and so on. And then look at R1 as a function of x1. And then maybe we have something that has a bit of a different pattern. And then we have another tree that will try to predict, that will then refine a bit the prediction. So typically the regions you will obtain at the next round will be different from the regions you obtained at the first one, and so on and so forth. So that's this idea of boosting is really that you try to fit with something that's simple, you take the residual, you refit by something else, and so on and so forth, and you add up all those trees in order to refine the prediction. And so there are generalizations to that, which I'm just, for the sake of time, hinting at, which is a gradient boosting. So in gradient boosting, what you're doing here is that you're saying that you're making some Taylor expansion. We're making a Taylor expansion in star. And then you're there to minimize something which is 1 over n L yi ft minus y xi, which somehow is a constant term and you don't care about, plus alpha over n, sum from I equal 1 to n, of partial derivative of L yi ft minus 1 xi. So that's more advanced material. If I'm losing you here, so be it, and there will be no consequences for what's next. So I'm considering the function which I'm minimizing there in the star problem. I'm doing a Taylor expansion with respect to this extra term I'm adding here. The idea being that if I have lots of terms, this thing that I'm adding can be considered as some form of perturbation. Then I want to minimize this as a function of alpha and theta. So I don't care about the first term that does not depend on alpha and theta. And so somehow this suggests that f x1 theta f xn theta, this vector should be more or less proportional to the partial derivative of y1 ft minus 1 x1, etc. Somehow I want my f my column vector of f's to be proportional of this column vector of partial derivatives of L, so that I'm going in this direction where I can maximally decrease. And to do that, typically what you would do is that you would you would take the difference and minimize it using trees. So the f's that are here, I mean the functions f which are there are you want them to approximate the functions that are over here. And so it's a regression problem that you're solving with trees. And that's what's behind gradient boosting. So here you do feed them using trees. I'm a bit vague here on purpose, I would say. And extreme gradient boosting is the same thing. So that's one method which is quite popular and extremely efficient. So I mean, not known in I don't think I've ever seen it in action in molecular simulation or quantum physics, whatever. But it's out there. I mean, where people have actually regression problems to solve and so on. It's really something that is extremely efficient and still widely considered with random forest and neural networks. And so it works similarly with the second order Taylor expansion. So you go one step beyond, but otherwise it's some similar idea, except that here you're making a second order Taylor expansion, then fitting the parameter alpha and also doing some trees to fit the gradient. You have also a random sampling of features. Random features as random forests. That's one thing. So I mean, at each round t, when you're trying to fit here the gradient, typically you don't allow for all the features at each node, but only random ones. That's always in the idea of increasing the randomness. And also you have regularizers for tree complexity. So instead of just limiting the depth, in fact, you have a term that penalizes the depth of the trees. And otherwise, lots of other tricks for making the method scalable. That was just somehow a teaser for ensemble methods to say that there are trees which are not so great learners by themselves, but then when you aggregate trees, you either with forests or with the boosting paradigm, you can get predictors that are really quite efficient and that can really be in par with neural networks. Voilà. But it's more again cultural because I don't have I haven't seen it in action in our field. Bon, last hour, essentially, we go to neural network. Yeah.
And you have alpha 1 and beta 1 and alpha 2 and so on. So imagine you have two sets, separate domains. You can make a good job for them separately. But in the first step, you were taking all of them. So you make a kind of average. So then if you go back, you see what I mean?
No.
So you had this ft minus 1. So you
Yep.
do it step by step. But then you could just go back and maybe realize that you did not.
I mean, it's the usual thing with greedy procedures. It's under-optimal overall. If you knew from the beginning that you had to have your predictor as a sum of capital T functions, what you end up with this procedure is not the optimum in general. But finding directly the optimum is computationally too complex. And so that's that's a doable way of coming up with something which is a sum of T elements. That's, I mean, greedy doesn't sound like a very positive term. It's because you want it to be as cheap as possible in the sense that computationally feasible and coming up with something that's reasonable as a predictor in the end. Well, you have specialists of greedy techniques in this room. I won't give names, but she's sitting by the window. So if you want... But yeah, no, it's really at something doable. And like trees overall, it's also some form of a greedy procedure for getting a partition. It's not the optimal partition, it's just one way of getting it in a feasible way. The highlight of the first 2 days, neural networks. I mean, I insisted on presenting as many other things than neural networks before, but you know, at some point you have to go to that. And so let's see what, I mean, I will be doing only feed-forward neural networks, or what's called the multi-layer perceptrons. So there are lots of other architecture now out there nowadays, like convolutional networks, graph neural networks, and so on. Geneviève will talk about graph neural networks this afternoon. Here I'm really considering the simplest ones, well, to discuss some general features of neural networks, and also because many ideas that appear for those simple neural networks, I mean, are still true for others. I mean, issues in terms of regularizations and so on, training, I mean, what is true here is true for others. So for neural networks, I mean, to set up the notation, I will be considering layers and various values at layers. So I mean, there will be layer little l equal 1. So here in this section, little l will index the layer. It will not be the loss function. That's because it's L for layers. And until you go to the end, and maybe to the end, maybe you have more than one output. Maybe you're outputting 2 quantities, 3, maybe a full vector like forces and so on. And I will be considering the situation where I have a fully connected neural network, which means that each neuron in one layer is connected to all the neurons in the next layer. So from a mathematical viewpoint, I will be considering variables here, which are, no, maybe let's, my prediction function f theta of x will be a composition of layer-wise functions, g theta 1 of x, like that. And I will denote by a little l what's happening from layer L-1 to layer L. And what's happening from one layer to the other is a composition of 2 things, an affine operation and the component-wise application of a nonlinearity. So here, AL-1, dimension-wise, it's something which is of dimension R DL-1. BL is of dimension DL. And so A0, my input here, I will denote it by A0. So A0 is equal to X. So that's something which is of dimension D. So I start with D0 is equal to D. Then I go to a second layer, which has a dimension D1. And for that, I'm taking my input and I'm multiplying it by a matrix which is of size DL times DL-1. Okay, and so this allows me to go for something of dimension DL-1 to a dimension DL. So that's this AL. And so until I go to the last layer where I have a dimension for the output, which is a D capital L. Okay, so I mean, the inside operation, I mean, it's an affine thing. So I take the values, the so-called activations of the neurons of the previous layer. I multiply them by a matrix. I add a vector B called the bias, but I mean, there's nothing to do with the bias in statistics. It's just that you shift the result. And then you apply this function component-wise. Well, that's called an activation function. And it's really applied component-wise. So if it's a vector, it's to all components of the vector. Typical choices for the activation. will be, I mean, historically, it was the 0, 1 loss. So that's the so for the perceptron, it was really the fact that you have this heaviside function of something being positive. From there, I mean, there were choices that regularized that. Then I would say 80s like you had the sigmoid function, so which would be 1 plus 1 over exponential minus z. So that's indeed something that's starts from 0, because when z goes to minus infinity, this goes to plus infinity, so sigma goes to 0. When z goes to plus infinity, this sigma is going to 1. So you see that it's something that regularizes this 0, 1 activation function. I mean, the perceptron, so the 0, 1, was really motivated by biology, you know, that a neuron is either activated or not, or deactivated in the brain. And so there was really this 0, 1 kind of behavior. Training then, I mean, doesn't sound like a good idea, because you do realize that at some point we'll need to compute a gradient of f to do some optimization of the parameters, and taking gradients of things like that is not really great news. So that's why people started to have regularized forms for that. This or a hyperbolic tangent. That's another choice. Then it's between -1 and 0, or -1 and 1, but you don't really care because of the shifts b and so on. It's essentially equivalent to the sigmoid. I mean, then affine transform between the two, so you have the same expressivity for the networks. Check. So those were, I mean, typically the default activation functions in the 80s. The issue is that you have a saturation of the gradient. So typically the derivatives here, the derivative of the sigmoid is really small when you're away from 0. And so this makes the training of deep neural networks with lots of layers particularly difficult because the gradients are saturating, and so you cannot really move the parameters. So that's why it was really 80s when you have a few layers, and nowadays popular one would be like a ReLU activation function, which would be the max between 0 and z. So which is something which is more like that. Good thing with ReLU is that in the positive part, the gradient is not saturating. It's constant, equal to 1, so that's particularly nice. But in the negative region, it's still saturating. So then people improved upon by considering leaky versions of ReLU, where you have a small slope on the negative side. And then others said that, okay, but it's not regular, so let's consider a GLU, so like a smooth approximation of ReLU and so on. So there is a whole zoology of activation functions here. And so there are many other choices. There is there are a few, I mean, at least a full section, a long section in the book by Bengio, Courville, and Goodfellow. So, I mean, if you want to really, Goodfellow, if you want to really know more about neural networks, that's really the reference I would recommend. It's from 2016. By the way, there are various textbook references and my full set of lecture notes on the web page of the conference. I don't know if everyone has seen it, but it's there. And so if you want to really know more about neural networks, that's the book I would recommend. Although it's from 2016, there are still a lot of things which are particularly relevant. And if you read the chapter on activation function, you'll have statements like, essentially, the activation function does not change so much the behavior of the predictive behavior of the neural network. if it's chosen in a way that you don't saturate gradient and you can still train the model. Voilà. So I mean, so that's I would say those are the activation functions that you have here, and maybe at the for the final output. Here for regression, you would have just a linear rho L of Z is equal to Z. So at the last layer, you're not doing anything. You're just predicting this. You're just returning this W capital L minus W capital L A L minus 1 plus B capital L, because you're doing some regression. So you don't want typically to restrict the range of values that you can predict. If you had other machine learning tasks like classification, maybe the last, you would have other activation function at the last layer. So if you are in the framework of logistic regression, when you do classification, maybe you want to have a sigmoid at the last step because you're trying to predict a probability, which then you will threshold to say whether it's a 0 or 1 that you're predicting. And so last layer is a bit different, depends on the task that you have. And otherwise, typically, in the core of the neural network, it's often the same activation function everywhere, although you could change it from one layer to the other. Just that at some point, there are so many choices that you need to make it a bit rational and you make choices in life. Is it fine overall for the structure, everyone? So that's how it works. So I mean, it's really a composition. I mean, it's really this composition of affine transforms and nonlinear transforms. Alors, so first thing maybe there is well, I don't do it here. I don't know whether you've played around with it, but I mean, there is something called the TensorFlow playground. Who knows about that? And so I mean, it's really those of you who know have an idea of how fun it is. I mean, it's a website where you have those little examples, and you can come up with with some neural networks and train them and see how the models are being trained, and then you see links which are more or less large as a function of the various networks and how you're making predictions in the end. So it's particularly nice to get a feeling of what is happening in the different layers. In particular, when you do classification, then you see the values of the neurons, what the values of the neurons are depending on the layers and which features are being learned. And you can also play with regularization terms and see that if you have strong regularization, then you're deactivating some units and so on. So it's really a good thing to have some feeling of what neural networks are doing and go slightly beyond the black box kind of feeling that you get when you use them. So if you haven't done so, I mean, I really recommend playing around with it. I usually take half an hour in my lectures to do so. I mean, somehow students have to stop me from playing around with it. So maybe a word on mathematical approximation properties. I mean, it's a somehow too simple a result, but still a result that is there to tell you that neural networks can learn any can represent any function. So it's a representation result, which essentially tells you that any continuous function can be arbitrary, can be approximated with arbitrary precision. So any continuous function, let's say on a compact set to simplify the proof, can be approximated with arbitrary precision with a neural network of depth 1 and ReLU activation of depth 1 with one hidden layer and ReLU. So this I'm actually going to prove. It's a simple construction, so I'm actually going to make it. So the first, so I'm going to consider an interval like minus r. And so that's here we have a continuous function. And so what we're going to do is we're going to divide this interval into various subintervals and then approximate this continuous function by a piecewise linear function. So here there is a first mathematical result is that by considering a partition that's sufficiently fine, you can always do that with arbitrary precision. I hope everyone is going to admit that in the room. Otherwise, no, we'll have a private discussion after the lectures about that. So first step is that you replace your continuous function by a piecewise affine function. And so the game is, can we represent any piecewise affine function with a neural network? And here I said representation, meaning that it's different from finding it in practice. What I mean by that is that in principle, there is a neural network that does the job. Now, whether when you actually train your model with some optimization procedure, whether you actually find it, that's another story. It's about whether you can really find that function. But at least it exists. And so the way it's done, we say that if we have m minus 2 kinks, this can be represented with a hidden layer of size m. So by m minus 2 kinks here, it's kink 1, 2, 3, 4, etc. until m minus 2. So for that, so first let me consider the case when f minus r is equal to 0. And we will see that in this case, we can do the job with a hidden layer of size m minus 1. And then by adding just one neuron, we'll be able to cover the general case. So we start from the situation where we start here from 0. And so then the idea is that if we start from 0, our function looks like that on the first interval. You start here from 0, and you go to some value at x1. And so that's particularly simple to represent with a ReLU activation function, because then we have that f of, I'm trying to keep the same notation here, x1 plus x plus r plus, so maybe it's yeah. So this plus thing is the ReLU activation function. So z underscore plus is the maximum of 0 and z. And I realize that there is a typo. So that's what we have on the first interval. Now on the second interval, we have a piecewise affine function. So it's doing something like that. It's going from x1 to x2 with some slope. So that's on minus r x1. If we are on x1, x2, f of x is equal to that very same thing, x plus r plus, and then we are adding a term to get the correct slope. So let's say we are adding a term like plus v2 x minus x1 plus. So maybe let me call those points like capital X1, capital X2, the grid I'm using. So what I'm saying here is that on this second interval, I'm adding this affine function so that the sum of those two affine functions is exactly the one I want. And after that, you just go on. Every time you see a new interval, you add a new affine function like that. And so in the end, you indeed have a neural network where you have just this one entry x, then you have your hidden layer here, and then you combine in the end. And if I want to be more precise here, I'm looking for a function f of x, which is the sum for j equal 1 to m of eta j wj x plus bj plus. I mean, I really have, I'm really constructing a function, a prediction function of that form. And that's exactly what I'm getting with a neural network like that, where I start from x. Then I do this affine transform. I'm applying the nonlinear function de ReLU, and then I'm gathering and using a linear activation for the end. And here I don't even have to add an extra bias. Yeah.
What value do you handle the case for f minus r?
I'm coming there.
You know.
Yeah. I mean, there is a 1, you're eagerly waiting for the 2. But so, I mean, is it fine for this 1K when you start from 0? And then when you don't start from 0, then we use the fact that 1 over 2r x plus capital R plus 1 over 2r of x, sorry, minus x plus r plus is equal to 1 on minus rr. I'm really just using that thing. Which can, I mean, here this x plus r plus is just equal to x plus r, and r minus x is also r minus x is also always positive. So you're summing them up and you just end up with 1. So this shows that you modify a bit the coefficient for the first term and you add an extra 1, and that's how you can represent the function with m elements in your hidden layer. Because here I haven't gone here to the end, but essentially if I have m minus 2 kinks, I go until x m minus 2, and so in the end I have been using m minus 2, m minus 1, I mean there are m minus 1 intervals. So there are m minus 1 terms, and then I'm adding an extra 1. So I mean that's a simple argument. I mean those kind of representation results go back to the 70s with Sibenko, who was the first one, I think, to show that you can represent any continuous function with a neural network. And then there are lots of extensions in terms of those representation results.
You have a similar result if you increase the number of layers, but you fix the number of...
That's less clear. I mean, the results are really about like wide layers, indeed. The deep kind of extension, which is more relevant nowadays because you're really going deep and not so wide. I mean, that's still, in my opinion, I believe that it's not, we're not there yet. Huh? There are some partial results. I mean, I'd recommend the section in the book by Francis Bach on that topic, but it's not as clear as that one. And it's more complicated because of the compositions, obviously. So, I mean, that was a result to somehow show that neural network have a really can be really expressive if you increase the number of degrees of freedom. And so maybe now is a good time to count the number of degrees of freedom. Number of degrees of freedom. Just to give you an idea of how many parameters you have, and it's a computation I find enlightening. So the example I like, it's a typical example of, it's like the default example in machine learning. So for molecular simulation, we have alanine dipeptide. I guess that for quantum computations, there are also some kind of small test systems like water or whatever, that is always the first method in the numerical sections. In machine learning, this default example is the MNIST dataset, which dates back to end of the 90s, and Yann Lequin was involved in that. So he was still believing strongly in neural networks at the time. No one was caring about them, and that's what made him famous afterwards. So the MNIST dataset, it's a set of 28 by 28 images of digits. Maybe you've seen then those images of from 0 to 9s. And it's when I'm saying it's an image, it means that technically, I don't know how much you know about images, but it means that it's a matrix of size 28 by 28. And each of the entries here, it's a number, it's an integer between 1 and 255 that determines how the intensity of the pixel. So 0 is white, 255 is black, and then you have all shades of gray in between. So 255 shades of gray. So in the end, it's just a big vector, if you think about it, a vector of 784 entries. And typically, one thing is that this can be binarized, so just 0, 1 per pixel, or maybe you transform it into a number between 0 and 1. Okay, so but at least the input we have is something of size 784. And when we do a classification, typically we want to return something of size 10 because we have 10 classes, 10 digits. And so we essentially want to predict a discrete probability, which would be a probability that the input is one of the digits. And so let's think about just having one hidden layer in the middle, something of size little l. So essentially, that's the simplest example one can think of in machine learning when you're trying to do a classification on this really simple data set with a neural network with a single hidden layer. And so the formulas we have for that is that to go from one layer to the other, maybe let me recall the formula that AL is rho L, WL, AL minus 1 plus BL. So here you start from something which is in dimension DL minus 1, and you go to something which is in dimension DL. So you need a matrix here which is of size DL times DL minus 1, and you need a bias vector which is of size DL. So the number of degrees of freedom, will be the sum of DL minus 1 multiplied by 1 plus DL for all your hidden layers. So here it would start at L equal 1 until capital L. And so for in this example here, if say little l is equal to 50, so maybe D1 here equal 50, which something that's in between 784 and 10, and rather on the smaller size. The final formula is that you would have D1 1 plus D0. I'll let you check that one. this will be the number of degrees of freedom, and you would have 3,900, so about 40,000 parameters, just with this simple neural network where you have one hidden layer, which is a lot, especially compared to the size of the MNIST data set, which has 60,000 entries in the training set. So that's an example that you see that immediately on the simplest example of machine learning with the simplest possible model, somehow you already are in a situation where you have almost as many parameters as elements in the training data set. And in many situations, you have in fact more parameters than entries in the data set. Just because here the complexity grows pretty fast because of this term DL times DL minus 1. You see, if I'm adding one more layer, then we start to have lots of parameters. So that's an important message to have. I find it always useful to have in mind how many degrees of freedom you are playing with, and compare them to the database. And usually, it's a bit scary, which definitely calls for thinking about regularization, capacity control, the fact that you don't really actually have 40,000 parameters to fit, but you want to restrict this to some extent using some form of regularization. Check. So, any question at this stage? So training neural networks. So typically we want to minimize our loss, which would be like the usual regression loss. So f theta of xi squared plus possibly plus lambda times some omega theta term. And so for a theta parameter. And so when we do that, we'll talk about gradient methods a bit more in detail tomorrow. Enfin, we'll say elements about that tomorrow. Today, if we have time, but I doubt it. We typically need to evaluate quantities like that. So the gradient with respect to theta of this f theta of xi. It's like a optimization method, and we'll be using stochastic gradients. So we'll need that, and definitely sounds like a complicated thing because there are lots of parameters, and some parameters are deep down in the model after a few layers. So when you need to compute the derivative of the output with respect to some of the parameters. So typically, if you think about neural network, I mean, to have a feeling of what this is, imagine a network like that with a certain number of hidden layers. And typically, you would want to know what, c'est pas comme ça, évidemment. You would want to know what happens to the output if you change a parameter here, in the connection from the first one to the second one. So somehow you have to propagate the change until the end and compute this gradient. And you have to do that for all of them. So historically, usually that's a part that takes me an hour at least, because I'm really explaining how it works. Here I'll be extremely brief. I'll just say that there is a method called backpropagation for computing those propagation to efficiently computing those derivatives. Essentially, you're evaluating the neural network forward to compute all the quantities, and then you're also evaluating some quantities backward to get the gradients. So it's like a two-kind pass over the model. So that's, I mean, it's a historic thing that really, I mean, neural networks could be developed thanks to that. Otherwise, you would not be able to train them. So someone had to come up with an efficient way of computing those gradients and something that can be implemented easily in practice. But that's, I mean, backpropagation is really limited to those feed-forward neural networks because it's really chain rule. And so it's an efficient way of evaluating the chain rule starting from the end and going back to the beginning.
The same principle in automatic differentiation.
I was going to say that nowadays people don't do that, but they actually do automatic differentiation. And this works, I mean, this does not require you to implement expression of the derivatives. I mean, that's typically what you want to avoid with automatic differentiation. First, because, I mean, it's less prone to errors if you're not implementing formulas, but you know, you physicists and chemists, I know that you can code up things and then you'll do all the debugging that it takes to have the gradients correct. Still, if you don't need to do it, it's a good idea. And it also, and maybe more importantly, extends to other kind of architectures. So nowadays in neural networks, you have architectures where you have so-called skip connections, where one neuron can be directly fed to a layer after the next one, like in ResNets and so on, and there are all other sorts of architectures. Graph neural network, we'll see this afternoon, convolutional ones, and so on. And for those neural networks, you typically don't want to think about writing down the derivatives. And that's where automatic differentiation is really handy. So for those of you who don't know, automatic differentiation is when you have like an arithmetic operation. It traces the computational graph. So you know, like you have x1 and maybe let's do an example for automatic differentiation. If you want to evaluate a function which is x2 exponential of x1 multiplied by square root of x1 plus x2 exponential of x1, and at that time, you know, I want the gradient with respect to x1 and x2. So of course, everyone is eager to do it by hand, but you know, let's refrain ourselves for a moment and let's write the computational graph. So first thing is that here you're first doing an exponential x1. Let's exchanging. So first thing is that you're doing an exponential to transform x1 to exponential of x1. So maybe let's put them inside the bubbles. That's the first thing. And then you're multiplying x1 and x2 together. And here you get x2 exponential of x1. Up, and then you're adding x1 to it. So here, up, you're adding x1 to x. The product. Sorry, to the product. Voilà. So here you have x1 plus x2 exponential of x1. After that, you're taking a square root. Well, you have something that I can start having trouble writing in my bubble. And this you're multiplying with what you had here. Well, my computational graph is a bit messy. I'm hoping computers do a better job. But this gives you an idea, you know, how to get the derivative of this with respect to the inputs. You have to look at the influence of changes of the inputs on all those elements. Some of the elements it directly relates to, and also the elements which are within the path towards the end. And so what automatic differentiation softwares do is that they typically construct this computational graph at compiling time or evaluation time, and after that they automatically get you the derivatives that you need. Voilà, so I mean, that's why I don't bother you with backpropagation, because anyway, in practice, that's what you should be doing, and that's what's being done in PyTorch and other kind of softwares. Software like that, by the way, I mean, mostly work with PyTorch, but I work. The people I work with use PyTorch, and sometimes, and I use PyTorch in my hands-ons. Otherwise, there would be, there used to be Keras, but it's a bit less in fashion nowadays. And there is also TensorFlow if you're really a C++ fan and have a lot of time to spare to understand how this is being constructed. For molecular dynamics, PyTorch I find is a good compromise because most of the software now interface with PyTorch. So either direct MD packages like OpenMM or other packages that do transition between MD and other things like Plum recognizes PyTorch, and so that's That's fortunate for us, let's say. Oh, JAX, yeah, I mean, typically it's even better nowadays, JAX, because it's automatic differentiation is much better there, and you can write MD codes and run them directly with neural networks and so on in there. The unfortunate thing I would say is that in terms of if you use an actual MD package like GROMAX and so on, like historic ones, the interfacing with JAX is still not so much better than PyTorch. But in JAX, I mean, if you have a simple MD code to write, indeed, that would be the way to go. Optimization. Do I say? So let's say a few practical things. It's a bit of a list that these are all the things that maybe you'd prefer not to think about when you're using neural networks and or that you're not forced to think about.
So you can differentiate essentially that differentiate at the level of the compiler by
yeah. And so I mean for neural networks it means that you have something that evaluates a neural network and somehow automatically give you those kind of gradients with respect to theta or x.
Can you integrate the same way? Because now you want the gradients because that you wanted to optimize. But assume that you have neural network, but you want to integrate it because, for instance, you learn a derivative. Can you do it?
Yeah, I mean, here it's really the automatic differentiation and so on. It's really how much the result depends on the input. So it's more like a sensitivity kind of thing. The derivative works that way because you're changing a bit the output. Integration, it's not really like that because you're summing up function values and so on. But yeah, I don't know the counterpart of that for. So a few practical things. I'd say that there is something about avoiding saturation of gradient. The gradients can saturate two ways. They can either vanish or they can explode. And because somehow, I mean, it's more clear when you see the backpropagation algorithm, but essentially you're composing functions. So when you're taking gradients, you're multiplying things. And then when you multiply things, they can either exponentially grow or exponentially decrease to be sketchy. And so you want to avoid that. And so there are various tricks for that. I mean, some people would say that, I mean, maybe you need to clip gradients to prevent them from being too large. So if they're too large, you just saturate them off. You use activations that do not saturate, activation functions that do not saturate. There are also things called batch normalization layers. Batch normalization layers, which I'm not discussing too much, but I mean something that standardizes the activations in one layer and then adds a multiplicative factor and a bias to in order not to limit the expressivity. But it's something that stabilizes the numerical behavior of the training. Check, and then you have skip connections. I mean, typically when you have skip connections, you're closer. I mean, here the input x1 here, it's closer to the end thanks to the fact that it appears here. And so when you have those kind of skip connections in a network, the impact of changing a parameter from one layer is felt more strongly about the output. So when you have those kind of connections, then it helps gradients to behave better. So that's one thing. There are issues about initialization of the networks. In order, I mean, the typical way neural networks are initialized is by a random, it's randomly. So it depends a bit on the activation function. But typically you have some some random initialization. And here what you have is that typically the variance of the random numbers that are being used is proportional to something like the number of incoming plus the number of outgoing connections. So if you have a neuron that's connected to a lot of other neurons, the weights and the biases it has at initialization typically are random numbers with a smaller variance. So the reason for those formulas, essentially, it's because let's think about a caricatural situation where it's MAM, something like that. No, maybe let's do it at the first layer. Let's do know what happens at the first layer when you have have a neuron that's connected to first layer, any layer. Let's consider something which is like a finite linear combination of n in elements. So the x's, I'm thinking about them as deterministic quantities, but the n's, I'm thinking about them as random quantities, so say Gaussians of that form. Or maybe I'm also considering the x's as being independent, random, but with some distribution, which some variance which will be of order gamma. And then the point is that this G here, the variance of G will be the number of incoming connections multiplied by gamma squared, multiplied by sigma squared, multiplied by gamma. And so in order for it to be of order 1, this means that typically sigma squared should be as should scale as 1 over the number of incoming connections. So that's the rule of thumb that tells you that if you don't want the quantities that appear in the neural network to degenerate, you should really use those kind of scalings. So that's when you do like a forward evaluation. And then in the backpropagation algorithm, what you see is that when you compute gradients, you in fact also need the connections from this layer to the previous layer. And so that's the moment where you have similar expressions, but then a sum with the outgoing connections, and that's how you end up with formulas like that. So typically, no one really looks at how neural networks are initialized, but depending on the activation functions, there are various rules of thumbs for correctly initializing them with Gaussians, uniform numbers, and so on, and with somehow precise rules for the variance. And if you don't initialize them carefully, typically gradients are completely crazy at the beginning, and you cannot really train the models. Also, as side remark, there are a lot of random initializations in PyTorch, and I know that it's really a trouble to have a fully reproducible computation. So if you fix the seed, and the seed of the random number generator and the seed of lots of other things, still maybe you won't get twice the same result when you rerun the method. So it's really a challenge to have something that has a deterministic outcome with PyTorch.
Instead of the same results, you mean like if you look at the parameters one by one, they will be different, but the overall performance.
Yeah, no, it's similar, but it's not exactly the same result, and that's yeah, that's because there are a lot of random things that are initialized and that you're never so sure how they are. And one last point is regularization. And so for regularization, I would say there is a ridge lasso under combination, something called elastic net. And there is something that's specific to neural network that's called dropout. And there will be a last one, which is early stopping, which we will see tomorrow. So it's an optimization procedure that already automatically regularizes the training. So dropout, the concept is that you randomly switch off some of the neurons at training time. And so when you switch off a neuron, you switch off all the incoming and outgoing connections. And the aim of that is that you want to avoid neurons to co-evolve. So somehow, it's like the bad student kind of model. When you have a group of students, they share up the work, and one is really specialized in question 2 and can do anything that's related to organic chemistry. The other one can do anything about electrochemistry, and in the end, no one knows how to do everything. So here, sometimes you randomly switching off a student, and so they need to be prepared all for all questions. And neural networks work out the same somehow. So let's be in this situation. So let's imagine that in this layer, I have a certain dropout rate. So in my training procedure, what I will do, training will discuss it more tomorrow. But at the training procedure, what I'm doing is I'm saying that in each layer, I've got a probability to drop out one of the neurons, say 0.1, 0.2, something like that. So I go to each layer and I'm saying that, okay, let's forget about that input here. Let's forget about this middle neuron. And then up, and maybe here I'm not forgetting anything. And of course, you don't deactivate the last one. And so then you're in a model where the only connections you have, so you only have 2 neurons in the second step here. Tac, voilà, comme ça. And then you have all those connections there, and then you go to the output. So here I've deactivated 2 of them, so their parameters will not change here. So that's training time. Not at validation, not at evaluation time. So when you evaluate the model, so either for validation or a test, you reactivate everyone. So you deactivate those units, and then you do one update of your gradient method. So you update everyone's parameter, and then next step, you randomly deactivate some units, you reactivate the parameters of the non-deactivated one, and so on and so forth. So that's a strategy, a regularization strategy that's really specific to neural networks. And it typically also leads to training losses that are larger than validation losses. And that's something that could seem a bit surprising, that we have seen exactly the contrary when adding extra terms, penalization terms to the loss. Then, well, typically training loss would tend to be smaller than a validation loss. But here, when we do a dropout, typically the model is less expressive at a training time than at evaluation time. And so that's why you can have training errors that are above validation errors. But anyway, in the end, it's validation error that matters. So it's just a way of preventing too complex, the network of being too complex. And so dropout is characterized by a rate between 0 and 1. And it's the usual kind of validation paradigm. You don't know what the dropout rate should be, so you just try out different values, and you do some cross-validation to find the correct dropout rate. Voilà. And so that's what you do at training time. You don't, and when you evaluate, then you restore everyone. Well, and that's about it. Did I have anything else to say about that? Nope. Up. Check.
Some sort of weight rescaling, right?
Meaning the fact that I'm deactivating things, do I rescale the weights for the others? No. So it really has to do his job like that. Alors, so I mean that's more or less what I wanted to say about. I mean the general thing about neural networks. Because in the end, I mean, once you know the form of the function, more or less everything is being said, except that in practice you have to find it. So maybe I'll just start a couple of minutes on optimization methods. And that's really, I mean, what I'll be saying is more or less general, but it's particularly relevant. For training neural networks, for which you really have a complicated energy landscapes. So one thing with optimization methods, I mean, so we typically want to find a theta hat. I mean, we've seen that at various places. We typically want to find parameters that minimize some function. So something like an empirical loss plus some regularization term. I mean, that would be like a typical choice among what we have seen those days. This thing being like a sum from I equal 1 to n of some elementary loss function, which for us was the mean square loss. But if you were doing, say, classifications, it would be something else, f theta of itself. So that's typically the kind of function that you want to optimize. And let's, I would say, let's list a bit some properties of this function. I'd say that the first thing is that typically we have non-convex problems. I mean, it's really clear with neural networks. You have those really complicated nonlinear functions of theta, and there is no hidden convexity. Only a few models in ML are convex, like a logistic regression when you have linear descriptors. Then, okay, you have a convex problem, but that's that's about the one situation outside of the analytical case when you have a convex problem. So that's one thing. The other thing is that you may have a non-smooth, but potentially non-smooth problem as well. Potentially non-smooth. That's when you have, let's say, lasso kind of terms. And maybe the most important problem is that we're really high dimensional. And that's where, I mean, for neural network, it's clear. For this simple MNIST example, we've seen that we had like 40,000 parameters, and that's, that's something where ML people don't even blink, because to them it's really like a simple model. So here we're really talking about optimization in extremely high dimension.
Yeah. Do you have an idea the order of the dimension, like
like millions of parameters? Yeah, typically. Really depends on the size of your input and your number of hidden layers and so on. So that's but yeah, it extends really fast. So high dimensional, and the other thing is that you may have expansive gradients. So at least order n p. When I say expansive gradients, I mean two things. First, if you really insist on computing exactly the gradient of that function, the price will be order n because you'll have to go over all the data points. And so if you have large data sets of millions of points, you're in for a long moment. And the other thing is that even if you only have a relatively few data points, sometimes computing the gradient of this function f can be also pretty expensive. Like with neural networks, when you do automatic differentiation, it's heroic. And sometimes it's already heroic to compute the gradient. And so computing a second derivative like a Hessian is a bit out of the question. I mean, if you want ML people to faint at the sight of yourself, just ask them about the Newton method, and they'll mostly fade away. And so this calls for a stochastic gradient method. So gradient methods, because computing the gradient is already expensive, so you don't want to compute more than a gradient. So let's forget about second order methods. And the other thing is that we will work with stochastic methods where we don't exactly compute the gradient, but compute some unbiased approximation of the gradient based on mini batching. So that's the teaser for tomorrow afternoon. Yep.
That's the good order methods. You can approximately build the Hessian for the data.
I know you know so.
But then you cannot store the Hessian because it's too large. Is there a way?
Yeah, I mean, so in fact, there are some second order like methods in ML. You don't really need the Hessian. You need the Hessian applied to some vector, and so there are ways of. No, otherwise because it's like if you have 1 million of parameters, you just forget. But typically, it's not the mainstream thing. Second order methods. Voilà. On that note, I'm not standing between you and your lunch, and I'll see you tomorrow afternoon. Tomorrow morning, it's Geneviève.
Numerically, it's still a problem that's more computer power bonded than RAM bonded. Like you do a lot of small operation rather than storage.